Hello, in today's video I'll show how to build own AI agent coding harness in Rust. This topic is very interesting because currently a lot of AI agent harness is very popular in Twitter, like Claude Code, Codex, P, and others. So I decided to learn how to build it and to record a video to show how it works. So first of all, let's jump to the architecture and to learn what is this coding AI agent at all. So in coding AI agent, user usually uses CLI because CLI is the most simplest interface to interact with it, but generally it's just a backend system like state machine which executes some actions. So in this video we will consider like CLI as an user interface. So user uses CLI, passes some arguments. Next, new chat is started, and AI agent will send messages to LLM. LLM will return response for each request, and in AI agent we will have a loop where we will handle LLM response message, execute tools, and convert this tool results to LLM messages back, and again send results to LLM. So basically it's a loop. It's a loop here. This loop works until LLM will decide that it's enough to execute some tools on the laptop and result are good. So yeah, this loop will work. And finally, when LM will decide that no tools need to be executed, we will write AI agent result to a file like result file markdown, and also we will have artifacts like generated code with LM, and this process will end its own execution. Basically, if taking more closer look to this architecture of coding agent, we can observe that it's just React AI agent pattern, where we have orchestration prompt, we have connected tools which can be executed, and LLM based on the prompt in the orchestration will decide what tool to execute and will work in the loop. But in coding agent, our tools became like read and write tools for our source code. In the case of software which I will show you today, it will be only a shell tool which will allow execute any shell command with in my laptop, and it's enough to build coding agent. So again, coding agent will work like this. User sends CLI arguments to AI agent makes some decision and gives a result back to user. From the project architecture, it contains three modules. Core module, which is the most important module. This core module contains all logic for AI agent loop, tools connected to AI agent, and etc. And we have additionally a storage module which is responsible to store chats with LLM in durable storage. In our case, it's a file. I'll show you it. It's a separate model because in the future I'm thinking to make this project more interesting and maybe even work in cloud. That's why having modular architecture makes sense to make it flexible. And of course we have CLI. CLI, a model responsible only for user interface in CLI, which connects core and storage modules together and makes this application work. CLI is a dedicated model because again I want to extend this AI agent harness with GUI in the future. So in the future I see that I will have some GUI application which will orchestrate the core and storage modules, because CLI is just like a prototype interface for coding agent. So let's take a look to the code. The CLI module, it contains this main Rust file. It just configures application itself and executes application. By default, we are trying to read configuration from a home directory.config folder with Code subfolder and config.json file. Next, we have this application structure, which basically is context with dependencies, like dependencies container, which contains this AI agent, chat storage, some config links, and that's all. The rest of logic just reads application from configuration. So let's go to the most important part of this application. It's core module. We have here domain module. It's just like inspired by DDD. It's just a collection of structs which will be used to process AI agent request. This is chart, which contains like link to project configuration, like where project is located, what LLM need to use, and a list of messages which were used in this chart. Message can be a different type, so it can be sent from different role. It's like regular code for LLM application. We have role of message is system prompt, user message or assistant message, and also we have message types. Text message type is just text generated by LLM or sent by user. Reasoning is special message type sent by LLM, which shows like how LLM was reasoning to execute one or another tool. And tool message is call of a tool in our system. Tool result is just a result of tool execution. So it's pretty simple. The rest of code just converts one type to another type. And let's also see to the tool file and check what tools do we have. So we have only one tool, as I told, this shell tool or bash command, which allows to execute any bash command on the local machine. It has its own JSON schema. JSON schema is needed to send to LLM to show for LLM what parameters LLM can use, and some logic to parse parameters and etc. So nothing too special. But if we will open agent code, there is more interesting code. So how it works? If we will look to CLI, back to CLI, we can see that we are parsing arguments to CLI application. It's like prompt, chat ID if we want to continue conversation from previous chat, and output. This will be a file where I need to write a result. It's optional. It can be empty, so we don't need to pass it. But how it works? First, we are parsing arguments. Next, we are creating or getting existing chat. And next, we are executing AI agent. AI agent is executing on the chat which we created or read from previous chat. And if we will open it, we can see that it works in the loop. So here is a loop. Next, we are executing current chat with all messages in LLM, because there is nothing special. We just send a list of LLM messages to LLM to generate next message to know what to do next. And this code, LLM executor, is it just converts my domain messages, domain structs, to OpenAI messages, because currently Code supports only OpenAI, but in the future I think to add more LLM providers like Anthropic or onboard OpenRouter to be able to choose a bigger amount of LLMs. I'm especially interested in the this GLM 5.2 or Kimi models, which allows to have low cost and pretty good level of intelligence. But anyway, it's for future. But as far as I have plans for this, I decided to make it flexible and to have message structure specific for my application, but it means that I need to convert my domain message model to LLM specific message model. That's why here I convert messages from domain message to OpenAI message. But anyway, this LLM executor works like this. It just converts LLM messages to OpenAI messages, sends request to LLM, and return converted response to my message type in the application. And next, when we receive these messages from LLM, because theoretically for one message we may receive multiple messages from LLM, we need to execute tools, because some of these messages may have tooled executions. And if we will inspect this loop, it works like this. If we have some tool executions, so here, then we will continue our loop. If we don't have any tool executions, we will stop our loop and return result chat back to client which executes this AI agent. It's needed because every time when we are executing our tools or processing messages from LLM, we are modifying current chat, because in the loop, next call to LLM should use updated chat. We can't use origin chat, because origin chat next LLM will never receive its previous responses. So what next? Let's inspect how tool execution works. Here is execute tools calls function. We are spawning async. We are executing each tool asynchronously to make tool execution parallel and speed up our tool processing. Do not have sequential calls. That's why we use this Tokyo spawn function, which probably spawns green threads. And here we have this execute tool method. It just executes bash command tool, because currently application supports only bash command. So it parses arguments and executes here our command, and next return tool result. Of course, it's insecure, because LLM may send any shell command to execute anything, like RAM some files or expose some secrets, but for the prototype of AI agent harness, it's okay to have this insecure thing, because even with it, we will see how it works. And in next video, I will investigate and show how to make AI agent harness secure and how prompt injection for AI agent harness works. But it's not for today. Today is just let's make this AI coding agent harness works. So yeah, we executed our tool. Next, we are doing simpler. As far as we executed all tools in parallel, because LLM may generate multiple messages in the response to my one message, like multiple tool executions. In parallel, I'm executing these tools. Next, I need to await every of these features and modify my current chat with adding this executed tools to it. That's it. If no tools, if LLM decided that no need to continue tools execution, let's break our loop and return current chat. After returning of current chat, we have this thing. So here we return current chat in the result variable, and we need to make it persistent. We need to store this chat in our chat storage. So basically we are adding these messages, newly generated messages, to existing messages in chat storage and finish our execution. So let's look to storage crate and see how are we saving our charts and messages. So when I was building this LE code, I was thinking how to save messages in the local system, and I was considering use SQLite or JSON file, but SQLite doesn't allow you to have multiple processes which are processing multiple chats work efficiently in parallel, because SQLite has a file lock which will make this process execution sequential, and so in short, it's bad for performance, because if multiple processes will save multiple chats even not related to each other, one process will always wait for another process. And I don't see any reasons to add this performance bottleneck by design. That's why I move it to second option, like JSON file. And with JSON file, we have another problem, is that we can in JSON file write overwrite full JSON file each time when we are adding new messages. It's bad, because why I need to overwrite full file? That's why I was investigating and found that there is a pattern with name JSONL. We have every line where on each line we are saving one JSON object, and first line is always chat record. It's like a chat configuration where project folder is located, what LLM to use, and etc. Next line is another JSON object, which is message record. It's a message which we used to send to LLM or receive from LLM. So every time when we are sending LLM message from our laptop to LLM vendor, we are appending this JSON record at the end of the file. Every time when we receive a message from LLM, we are appending this message record to the end of the file. So it's always, we are not overriding full file. We always append new data at the end of the file. So it makes it efficient. We don't have any lock between independent processes. We have only one requirement, that one LE session should work with one chat at one time. But it's okay. In majority use cases, it's okay to have one session for one chat. And for reading this chat and messages, we need to have special code, which will read first line as a configuration, and the rest of lines will be will be messages. So let's inspect it. As I told, we have like two chat record, which has two types. One is chat record is chat configuration, which contains project configuration, LLM, and created time, so it's only configuration. And next we have message record, which contains written messages. And when we are reading the chat, we are doing this, we are reading records. Like line by line, it just will be a vector of chat record, and first record will always be a chat, so we are converting it from the chat, and the rest of records will be messages. In this way we will create a chat from this file. And when we are saving chat, we are doing very similar. We are converting chat configuration to chat record, adding it, and all messages are going after this chat record. When we are appending messages, we are just adding this message records at the end of the file. And if you will look at this JSONL file, it will contain just generic code to read and write records to JSONL file. That's it, I think. What I can do, I can show you demo. Let's see what I have here. So we have this LE code. Okay, LE code. Let's say build Python server which will have 3 endpoints for students management system in the students folder. So it's just dummy example, but when we execute it, we see how our messages are going to the LLM. By default, it uses GPT 5.6 Luna. It's in configuration, like if no LLM is specified, use this LLM. And if we will open project folder, I have here another folder, management server. It's for my next video about security issues with current code base, which is on another branch. That's why you don't see any files here. But anyway, LE code created students folder here because I executed LE code from this management server. And here we have this Python file which LLM generated. Here LLM generated tests for this Python file, and and it will work. Also, it generated some README. So yes, AI agent harness works. Like, it's not secure, but it works. And if you will open this chats folder in config folder, we can see last chat which was created today to build a Python server. And here we can see that first message is system message. It's system prompt, which says you are helpful coding AI agent. I can show you it here. Basically, this is this first prompt. It contains like couple blocks like identity, who are you, and your instructions. I didn't optimize this prompt too much. I just wrote it from the scratch and tried to use it with GPT 5.6 Luna, and it worked. Ideally, I should build some prompt evaluation, but it's like task for the future. And here we can see that LLM executed multiple tools, multiple bash commands, and at the end it built this Python server. So it works in this way. Here we can see that it's firstly tried to execute like where it's located, like what is the folder, LSLA, and try to execute other tools. So like the same how Claude Code works, or OpenCode, or other AI agent harness. Yeah, that's it. It works in this way. Also, if you are interested, I open sourced this AI agent code, AI agent code harness. So if you will go to my GitHub, here is this repository Code, which contains everything what I was showing you. Also, I have an article about this agent harness. It's here. Link is in the repository. Basically, everything what I explained to you in the video is in this article. I will include links to the repository and article in the description of the video. I think it's everything. Thank you very much. Have a nice day. Bye.